All right. So today should be pretty short like yesterday was. We'll do a few problems here together, but I think we pretty much have all the information that we need in order to kind of complete this section. All right. So today, all right, we're going to be doing coordinate proofs using distance with quadrilaterals. So we're going to combine all of our stuff with slopes we talked about, parallel slopes, perpendicular slopes, all that jazz. We're going to add in the distance formula now officially, right? Unofficially, we've talked about it and said that, okay, we could use distance formula here too if we wanted to. But now we're going to actually have it show up, okay? And so we want to be able to answer the question today, how can you use slope and the distance formula in coordinate proofs, right? That's what we want you to be able to answer today. Okay? So we're not going to use this first page. We're going to skip, okay, to just our first problem here. So on page 538, page 538, okay, is where I would like you guys to kind of take a look here for our very first problem. And this one we'll just kind of look through. They already have it worked out for us. Okay? So example 1 asks us to prove or disprove. Proof. I hate proofs, Mr. Witt. That's okay. These proofs will be easy compared to the stuff we've done in the past, I think. Prove or disprove the quadrilateral determined by the points A, B, C, and D is a parallelogram. Right? This is stuff we've already been doing. So, letter A, option 1 here. One option, right, is to use slopes to write the coordinate proof. And so you can see they find all the slopes here. They get 3 and 3 and 2/5 and 2/5. So opposite sides are parallel. The slopes of opposite sides are equal. So this means opposite sides are parallel. So quadrilateral ABCD is a parallelogram, right? Bing, bang, boom. Very easy. All right. So there's that. All right. We know how to do that, though. That's pretty easy. Alternatively, right, what's another property of parallelograms? What's another strategy we could use here? How else can we show this shape as a parallelogram? What's true about the opposite sides of a parallelogram? Besides them being parallel, they also must be what? Congruent. Exactly, which means we get to use the distance formula 4 times. All right, so let's do that here. So let's see, I'm going to try and, can I make this easier? Maybe I could do this. Okay. So I'll do this to kind of help us out here some. Okay, so letter B, because it says use the distance formula here. So we're going to find the distance from A to B, first of all here. Okay, A to B. And so let's see here. So the distance formula, remember, is the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. All right, that's our distance formula there. So from A to B, so A has coordinates 4, 4, B has coordinates 3, 1. Okay, and so it looks like they use, there should be a 3 here. Okay, 3 minus the 4 squared plus 1 minus the 4 squared. Okay, so 3 minus 4 is negative 1 squared. 1 minus 4, negative 3 squared. And so negative 1 squared is 1 plus negative 3 squared, which is 9. So it's going to give us the square root of 10. Okay, so AB is the square root of 10 there. Okay, do the same thing here with BC. Okay, so from B to C, they did the x-coordinate negative 2 minus, and then the other x-coordinate of 3. Okay, and then it's going to be negative 1 minus the y-coordinate of 1 there. Okay, so negative 2 minus 3 is negative 5. Negative 1 minus 1, negative 2. Negative 5 squared is 25. Negative 2 squared is 4. So it's square root of 29. Okay, right. Scooting down here. See, can I get it all to fit? Yeah. All right, and then from C to D, okay, so D is negative 1, its x-coordinate, minus negative 2. And then its y-coordinate is 2 minus then negative 1 for C's y-coordinate there. Okay, so negative 1 minus negative 2 is really plus positive 2, so we get 1. And then 2 minus negative 1 is really plus positive 1, so it's 3 squared. 1 squared is 1, 3 squared is 9, so 1 plus 9 is 10. So there's that. And then finally, dA, okay, A is 4 minus negative 1, the x-coordinate for D, and then 4 minus 2, the y-coordinate for D there. So plus positive, so you get 5 squared. 4 minus 2 is 2, 2 squared, and so we get 25 plus 4, which is 29. Okay. And so, and again, they have this kind of fill in the blanks here. We can just say something like this. Since opposite sides are equal, ABCD is a parallelogram. Okay? Did we have to do both of these to show this thing was a parallelogram? Do we have to do both of these things? Do we have to show that opposite slopes were the same and that opposite sides were congruent to show this thing was a parallelogram? Do we need to do both? No, right? We only need to do one to show us a parallelogram, but Mr. Woodmeyer just likes to torture you. And so there we are. Torture complete. Well, not really. We still have some more notes to do, so, right? Some of you guys are like, yeah, we still have the whole school day to go through. That's torture enough, right? So anyway. For your turn here then, so I'd like you guys to try one now, all right? Pick one, 4 or 5, your choice, okay? Prove that ABCD is a parallelogram, or prove that the diagonals of ABCD bisect each other. So either one. Of course, if you do 5, you also are technically doing 4, because if the diagonals do bisect, then ABCD is guaranteed a parallelogram. Likewise, if you prove 4, then you're guaranteed to also show 5, because if a shape is a parallelogram, then the diagonals automatically bisect. So really, by doing one of these, you're doing the other one kind of too. But anyway, pick one, 4 or 5, and just show it, okay? Your choice. So, let's go here to... All right, so Stephen, were you able to come up... Which one did you pick here? Did you try 4 or did you try 5?
I did 4.
Number 4. Okay, how did you try number 4? What did you do?
I drew it out.
Okay.
Graphed it?
Yeah. And then what'd you do from there?
I counted the slope.
Counted the slopes.
BC and AD.
Okay, so what'd you get for the slope of BC and AD there?
They were both 2 over 3.
2 over 3? Okay, and did you also do AB and CD as well?
No, I didn't do that.
Okay, so what would their slopes be?
0.
Yeah, 0, right? Yeah. So since opposite sides, right, are parallel, therefore the shape's a parallelogram. Yep, that's one way to do it, using your slopes. Anyone do number 4 in a different way? Madison, you did? You did! Oh, wow. You like to torture yourself, huh? I was surprised that someone picked it. So good. All right, so what did you get for your distances then?
A, B, and CD are the square root of 25.
Okay, what is the square root of 25?
5.
Just 5, so yeah. Yep.
And then BC and DA is the square root of 13.
Square root of 13. Great. Very good. Okay, yes. Nicely done there. Yep, it would be that. All right. So yes, alternatively, we could have done the distances there. So good for you. Okay. There I did the slopes. Oops, I'm going to cover that for you. Okay, so I gave the slopes too. Okay, but distances, awesome. All right. Good job. All right, how about anyone do number 5? Anyone try number 5? No? Okay, well, how could we show then the diagonals of ABCD bisect each other? What could we do? Avery? Midpoint formula, right. Okay, and specifically, what are we looking for? The midpoint of, so AC and BD. And then how do we know? Once we find those 2 midpoints, how can we tell if the diagonals bisect or not? If the midpoints are the same. So if we do that calculation, there it is, okay? If you do the midpoint from A to C, okay, A to C, that would be the diagonal, right? It's 4, 1. The midpoint of B to D is also 4, 1. So they both have the same midpoint. That means those segments bisect one another. Okay? Now, alternatively, like I said earlier, right, since we showed in step 4 that this shape is already a parallelogram, then in step 5, we can guarantee then, okay, well then ABCD, the diagonals must also then bisect, right? That's a property of a parallelogram. Right? So given step 4, we could just say, for step 5, we could have just said, see the work in step 4 to show that ABCD is a parallelogram. Since ABCD is a parallelogram, therefore the diagonals must bisect each other, right? So that's also a way to prove it without having to do any calculations there, right? Since we already established it's a parallelogram, we don't need to use the midpoints here. We could have just said, since ABCD is already a parallelogram, a property of parallelograms is that the diagonals bisect. Bada bing, bada boom. Okay? So your choice there. Again, alternatively here, again, it works in the other direction too, right? So, again, use your properties, right? Use your properties, I know these can take some time, so, but use your properties to help you out. All right, let's go to the next page here, page 540. Okay, look at some of these. All right, so, for example here, letter A asks us, so again, we're proving or disproving each statement about the quadrilateral determined by these coordinates here, okay? So you can see our shape right there graphed. We want to show the diagonals are congruent, and of course, to show diagonals are congruent, we're going to use distance formula. Okay? Folks, if you don't like using the distance formula, that's okay. If you want to here, you can draw these diagonals in. And then you can create like a right triangle here with the diagonal as the hypotenuse, right? So there's like a right triangle, leg, and then you can find the hypotenuse using the Pythagorean theorem, if you prefer, right? If you don't like that distance formula, that's okay. Just use the Pythagorean theorem there. It is the distance formula, right? But anyway, so use that, if you want to. But anyway, in either case, you get the diagonals are congruent, right? And so, we want to then prove that QRST is a rectangle. Okay? And they have us find the slopes. They found the slope of QR for us already. QR slope is -1/2. So we'll go ahead and find the slope of RS. So RS is up 1, 2, 3, 4, right 1, 2. So 4 over 2, which is 2. Okay? Slope of ST is down 1, 2, 3, and then right 1, 2, 3, 4, 5, 6. So -3 over 6, or -1/2. And then finally, the slope of TQ, that's also going to be up 1, 2, 3, 4, right 1, 2. So 4 over 2, or just 2. Okay, so there are 4 slopes. Knowing these 4 slopes, what can we guarantee this shape is? What kind of shape? Yep, Steve? Okay, so hold off on that.
Sorry.
That's okay. I see. Actually, you know what? I think you're right. Why would you say we can make it a rectangle here? What's your reasoning for that? You are correct. What would be your reasoning?
The slopes of ST and QQ, and they're both opposite of each other.
Okay, so they're perpendicular slopes, you're saying? Opposite reciprocals, and so therefore we have a right angle. Okay, so we have a right angle in our shape. That's right. What else do we know about our shape, though? What about the other slopes? For example, we have -1/2, 2 and 2. Okay, yeah. Okay, so right. So your reasoning there, Stephen, is almost right, but we have to first back up one step and say, okay, is this thing a parallelogram first? Once we establish the parallelogram, then your little addition will then make it a rectangle as well. Okay? Now, however, though, so it is a parallelogram, right? We have that opposite sides are parallel. We're actually done, though. We don't even need to check to see if it's perpendicular. Why? Because in the previous step, we showed the diagonals of QRST were congruent. Congruent diagonals is a property of what kind of quadrilateral? Congruent diagonals are a property of what quadrilateral? Avery?
If it's a parallelogram, then it's property of a rectangle.
Right, yeah. So if you have congruent diagonals, guaranteed that shape is a well, if it's a parallelogram, then it'll be a rectangle, right? And so here we go, right here, right? If it's a parallelogram, we just showed that, right? Then we already have this from the previous step. So together, it's a rectangle. Okay. So there it is, right? Already know that it's got congruent diagonals. We then say it's a parallelogram. These two together combine to make it a rectangle there. Okay. How can we show that this shape is not a square? How can we show that it's not a square? What could we do? It's a rectangle. How can we show it's not a square? What are some options? Distance of the side. So like find the distance formula for the side. So you can just show like ST's distance and TQ, show that they're different. Yep, that's one way to do it. What about the diagonals? What's going to be true about the diagonals of a square that won't be true about the diagonals of a rectangle? Preston?
Should they be like right angles?
They'll, yeah, perpendicular. They'll be perpendicular to each other. So an alternative way, if you want to use a distance formula, you could show just that the diagonals are not perpendicular. That's an option there too. Okay. All right. So again, let's on your turn there. You can pick whichever one you want. Pick 7 or 8. Okay, one of those two. Prove or disprove each statement about WXYZ. So for number 7, prove or disprove that WXYZ is a rhombus, and then for number 8, prove that WXYZ, the diagonals, are perpendicular. Prove or disprove those. Okay? minute here, one more minute, and then we'll go over these, okay? One more minute. Okay. Let's go to. Oh. All right, Emmanuel. Did you do 7 or 8, Emmanuel?
I did 8.
Number 8. Okay. So, how did you go about showing the W diagonals of W, X, Y, Z are? Or well, first of all, did you get it to work? Were you able to show the diagonals are perpendicular?
Well, I did the slope of WY,
Uh huh.
and then the slope of XD.
Okay. What did you get for the slope of WY?
3. Yeah, 3.
Was it
3/4.
3/4?
Yeah, 3/4. X. Or no, WY.
Okay. So yeah. So I'm sorry. What did you say the slope was from WY? The slope was what?
3.
3.
Yeah.
3. Okay. And what did you get the slope from X to Z?
-1/3.
-1/3. Okay, so I think that's right, but I think you're off a little bit with. Well, let me just go to here, right here. Zoom in on that. All right, so W, X, Y, Z are perpendicular, so I got XZ to be -3, and what WY to be 1/3. Is that what you got too? I think what you maybe did, you might have it's rise over the run. I think you did run over the rise potentially there. Like from W to Y, we go up 1, 2, 3, and then we go over 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 3 over 9. I think you did 9 over 3 there, I think. So you sort of the right result because you did the same thing twice, and so it worked out that way. But just be careful. It's rise over the run there. So you just got it reversed. That's okay, though. Well, I mean, not okay, but obviously you'll fix that. That's not a big deal. You got the right idea. Okay? Right idea there. Okay, good. And so then for number 7, okay, number 7, we want to show all the slopes for our sides, okay, and we have parallel opposite sides, and we have parallel or perpendicular diagonals there, and so then W, X, Y, Z is a rhombus, right? That's one way to go about showing that. Okay. How can we use distance formula? How can we use distance formula to show that this thing is a rhombus? What would we want to do for that? How can we use the distance formula to show this thing is a rhombus? Jenny, you have an idea? Could I never mind? I could. What can we do here? How can we use distance formula to show that this thing is a rhombus? Emma?
Find all the sides lengths.
Yeah, find the lengths of all the sides, right? Which is a lot of work, right? Distance formula, again, it's kind of messy, but it's not too bad since we have, these horizontal lines here. So that would be what? 5, 1, 2, 3, 4. Yeah, 5 and 5, and then you just use distance formula for those two and stuff like that there. That's an alternative there, okay? If we use that, so if I say, if we do what Emma said and just found the distances here, okay? Once I have that all 4 side lengths are equal, is that enough to say it's a rhombus? Or do I also need to have it's a parallelogram prior to that? I mean, right, there are some times when we need to show it's a parallelogram first, and then we do that like one extra property, and that makes it the shape that we're looking for, right? But if we only know that all the sides are equal here, do we need to show anything else to guarantee it's a rhombus? Right, so what's the definition of a rhombus? A quadrilateral that is what? Or that has what? What is a rhombus? What is a rhombus? A quadrilateral that is Luke. Equilateral, exactly right. So having all 4 sides equal guarantees it's a rhombus, right? No extra work needed. Okay, no extra work needed. All right, thank you, Luke. All right, so last thing here, and we'll just look through these real quick. I'm not going to make us work through any of these. We'll just get started on the homework right after we just look through this one right here. All right, so final thing, right, that we want to be able to do here, and we kind of already did this homework. We've kind of been doing this already, so it's not anything too crazy. But just in this example here, it's asked us to use the diagonals to determine whether a parallelogram. So in other words, this thing, we already are given it's a parallelogram. We don't need to show that. So given this is already a parallelogram, identify if it is further, if it's also therefore a rectangle, rhombus, or a square, and give all the names that apply, right? So kind of like the warm-up today, except from the warm-up, I didn't even tell you it was a parallelogram. So here we know it's a parallelogram. We want to then show it is whether it's a rectangle, rhombus, or a square, right? Okay, so knowing that this thing is a rectangle, knowing this thing is a parallelogram, and we want to use the diagonals, okay, given this thing is already a parallelogram and we want to use the diagonals, what about the diagonals would then make it a rectangle? So go ahead. They would be equal in length, right? Okay, you can look at the shape and see that's not going to work, right? And in fact, when you do the lengths, you can see 4 root 5 is not the same as 2 root 5. They actually do the distances there for us, right? Not the same. Okay? All right, so it's not a rectangle, right? Okay, rhombus. What would be true about the diagonals for if the parallelogram was a rhombus? What additional thing would be true about the diagonals? The diagonals would be what? Luke? Perpendicular. You got it. And it looks like they are perpendicular here. And when you find the slopes of the diagonals are opposite reciprocals. Okay, so it is a rhombus. Can it be a square? Why not? Because it's not a rectangle. It is a rhombus. Cannot be a square, right? A square has to be both rectangle and rhombus. All right, great. Okay, well, you don't have to listen to me talk anymore right now, right? So thank you for your patience. I know this is the third day we're doing this stuff, and if you've got it, you feel like I, apologize for beating into your head one more day here, but that's that. All right, so page 543 will be your assignment, starting on page 543. Numbers 3 through 6, 13 and 15. Okay. Show your work. Justify your answers. Okay. I do not want to see single word answers here. Okay. All right.